today's video, I would like to share to you how to configure a metro network to integrate with the IP backbone network to provide MPLS VPN service. In this topology, on the left side is the metro network, including CSG or cell-side gateway router at the access layer, and in the middle is AGG routers or aggregation, and the MTC router or the metro core. On the right side is the IP backbone, including ASPR, which is the border router connect to the metro network, P and PE router, and route reflector router or RR router. The metro network and core network are segmented to different AS systems, and within the metro, the access layer and aggregation layer are segmented into different OSPF area. The CSG router in metro core acts as a PE router connect to customer or to other equipment for different kinds of service. So on GSG, VIFs will be configured for different kinds of traffic. The CE here can be a router at the customer side, or can be the not B or E not B in mobile system. The same, the CE in the metro network can be a gateway to internet, or the gateways of a mobile system like EBG, MSC, or media gateway. Our purpose is to create an end-to-end VPN connection from CSG to PE router in the core network, to have CE-A2 communicate with CE-A1. So let's move on the control plan for the inter-AS VPN. Because the core network and metro network are in different AS systems, so in order to advertise VPN requests from one AS to another, a method called inter-AS VPN should be employed. There are different options. In metro network, we choose option C, with use route reflector in each AS to exchange VPN v4 requests. So the route reflector in core network will establish EPGP multi-hop VPN neighbor relationship with a route reflector in metro core network. The route reflector here is the metro core router. This router will act as an inline RR router. It means that it participates in both forwarding and controlling function. This metro core also acts as an ASPR in the metro domain to connect to the ASPR in the core network. So let's see how to advertise VPN prefix from one AS to another. For the VPN prefix from PE router in core network, then advertise to RR router. The VPN prefix then will be advertised from RR router to its EPGP neighbor, that is the metro core. So by default, because this is the EPGP neighbor, so by default RR router will change the next hop to itself. But our purpose is to create an end-to-end VPN. So we need to keep the next hop at the PE router. So on our router here, we need to configure the next hop unchanged. Next hop unchanged. It means that the IP VPN prefix advertised to metro core the next hop will be the address of PE router, not the address of RR router here. The same for the metro core router. When core router receive VPN request from the RR router, it will advertise to its RR router clients, which are AGG in the aggregation layer. AGG also acts as an inline RR router, so it will advertise the VPN request to CSG router, here. So when the CSG router receives VPN request from the core network, the next hop is the PE, the address of PE router. On the reverse direction, also the same. The VPN request from CSG advertise to AGG, then AGG advertise MTC or metro core. The metro core by default will modify the next hop to itself IP address. So we need to enable the next hop unchained on metro core so that it keeps the next hop to be the IP address of the AGG when advertising the IPv4 request to router in the core network. When the AGG advertise the VPN request to metro core, the next hop to set will be set to itself, not the IP address of CSG, because the number of CSs is very large. If we set the next hop on the CSG, we need to advertise the loopback IP address of CSG to the core domain. So the number of prefixes need to be advertised or need to be processed on the core network will be a lot. So instead, we will set the next hop for VPN request from CSG to AGG. Then we only advertise a small number of address on the AGG to the core domain. So when PE router in the core domain receive a VPN request from the metro, the next hop is the IP address of the AGG. But in order for the PE and AGG install the VPN request to their routing table, the next hop must be reachable. It means that from AGG can reach to the PE address. In order to do that, we need to advertise IPv4 loopback address of PE in the core network to route to the RR and then to the metro network, and also the IP address of AGG need to be advertised to BGP and advertised to the core network. The issue here is that we would like to establish an end-to-end LSP directly between the AGG to PE. But there is no MPLS on the link between metro core and ASPR. So how to advertise the label on the core domain to metro domain? Then we have to use BGP IPv4 plus label or RFC 3107, or in the Cisco iOS SR, we call this a BGP IPv4 label unicast. When we enable BGP IPv4 label unicast, BGP will advertise IPv4 request together with the label that the router assigned for that IPv4 request. Within each domain, we will also use BGP IPv4 label, because if we don't use IPv4 label, we have to redistribute the loopback address PE router in the core network in the metro core. We have to redistribute on metro core from BGP to OSPF, and on the ASPR it is the same. We have to redistribute the IP address of the AGG to OSPF so that the PE router here and the AGG can communicate each other. But when we use BGP IPv4 to reduce ASPR and the metal core router, when we use BGP IPv4 label unicast, we establish an end-to-end LSP that running across the boundary between two AS systems. So there are some key points here that in order to establish an end-to-end VPN from AGG to PE router, we need to enable next hop unchained on metal core router and route on the RR router in core network. And in order to establish an end-to-end LSP from AGG to PE router, we will use BGP IPv4 label unicast on the link between ASPR and metal core and within each domain. The third noted is that the next hop for VPN prefix from CSG to the core network will be the address, loopback address on AGG, not the address of the CSG. So in our topology, let's see how the prefix to be advertised. There are two kinds of prefix, IPv4 and VPN-v4. With the VPN-v4 PE router, we advertise to our router. Our router will advertise to metal core with the next hop unchained. It means that the next hop is still the PE router. A metal core then advertise the VPN v4 prefix to its RR clients, which are AGG router. AGG then advertise to CSG. For the IPv4, PE router advertise its loopback address to the RR router. RR router then advertise to ASPR. ASPR then advertise this IPv4 prefix to the metal core with a label that is assigned to this IPv4 address. Metal core also then also advertise this prefix to AGG router with label. These label are BGP label unicast label. So from CSG, when it want to communicate with the PE router here, the next hop will be the PE router in core network. So let's see how the data is forward between CE-A2 to CE-A1. The packet, when the CSG receive an IP packet from CE-A2, we check its VPN v4 label table, and in this table it said that if the CSG want to go to the destination address 10.0.1.1, that is the loopback address of P1 in the core network, it has to send the packet to the next hop at the address of 10.2.1.1. That is the IP address, the loopback address of AGG2, and it also adds a VPN label 24006 into the packet. Then the packet will be forwarded to the AGG2 using the algorithm interface 800 and with that LDB label. So the packet from CSG to AGG only has one label, that is the VPN label. At the AGG, when it receives a packet with the VPN label from CSG, it also checks in its VPN v4 table. In this table, it says that if it wants to forward the packet to the destination address of 20.0.1.1 of the PE1 router. It will send to the next hop at the address 10.0.1.1. This is the IP address of PE itself, and it will swap the VPN label using a new VPN label of 24005. The next step, HGG will look up an its IPv4 label unicast table, and it says that if you want to go to the next hop at the address 10.0.1.1, it will send the packet to the next hop at IP address 10.2.0.1. This is the IP address of the Metro core network, and using the label, another label here is 24004. This is the unicast label and advertised by the Metro core. And another step is it will check in its MPLS forwarding table. It want to go to the address of the Metro core. It will forward the packet out to the interface GI000 and using the LTP label of 16. This is LTP label. So the packet going out of the HGG will have 3 labels in its label stack, including VPN label, BGP unicast label, and LTP label. We'll see it here in the picture. The packet going out of the CHG has only one VPN label, and this packet arrived at HGG. The VPN label will be replaced by another VPN label assigned by HGG2 here. This VPN label is to PE router in the core network. And then from HGG2, if it wants to go to PE address at the core network, it will send the packet to the Metro core using a PGP label 24004. And the next step is it wants to go to the Metro core. It has to send the packet out of interface GI00 to the HGG number 03 here, and using LTP label of 16. So the packet going out of HGG number 2 has 3 labels. At HGG number 3, when it receives a packet LTP label, it will check and look at the MPLS LTP table, and it will remove the LTP label, the stack, and forward the packet to the MTC with 2 labels left. Because HGG is the last hop to reach the Metro core in the Metro domain. So before sending the packet to the Metro core, it will remove the LTP label. At Metro core, after receive the packet with 2 label, it will check in its PGP IPv4 label, and then it will swap the BGP label into a new label of 24003. This label is advertised by ASBR to Metro core. When the Metro core forwards the packet to ASBR, when ASBR receives the packet with BGP label, it will check in its MPLS forwarding table and then swap BGP label by the LTP label. Because inside the core network, ASBR can reach the PE router by the IGP protocol. Here is the OSPF. So from ASPR to the PE, we use the LTP label instead of BGP label. And ASPR then forward the packet to P router. P router will remove the LDP label and leaves only VPN label, because P router is the last hop to reach the P router, so it will remove the label before forwarding the packet to P router. P router, when receive the packet with only VPN label left, it will check, it will remove the VPN label and forward the packet to CA1. So that is the flow to forward the packet from CA2 to CA1. So that is enough for theory principle. So let's move to configuration. Now we will configure the metro network to provide MPLS VPN layer 3 to connect the CA2 to CA1. On the CHG, we need to configure VIF and apply to the interface connect to CE, and the same for PE in the core network. For simple, there is no routing protocol used between CHG and CE. Here we will use redistribute to redistribute the connected IP address into VPN v4 on the CHG. In this lab, the IGP protocol or OSPF we already pre-configured, so no need to configure OSPF anymore. We only need to enable MPLS on the interface of the router CHG, and then configure VPN v4 EPG neighbor to AGG. On the AGG, we need also configure the neighbor towards CHG, and AGG act as a route reflector, and AGG will configure the neighbor relationship to metro core router for VPN v4 and IPv4 label unicast. On the metro core, need to configure BGP IPv4 label unicast with ASPR and VPN v4 BGP multi-hop between metro core router and RR router to exchange VPN v4 prefixes. The ASPR need to configure BGP IPv4 label unicast to RR router to receive IPv4 prefix advertised from PE router. RR router configured IPv4 label unicast to PE router and VPN v4 to PE. So now let's start with CHG. And now we configure VIF. Let's take the name for signaling for VIF. The route distinguisher is the column 1. We use route target for both import and export is 65101 column 1, and then we apply this VIF to the interface E0/2 towards CE. Then reapply the IP address for the interface. That's all for VIF. And now we need to we will configure BGP. we configure the neighbor to AGG using peer group. We will use a loopback address of AGG for neighbor establishment. We only need to activate VBN v4 towards AGG. And then we need to advertise or redistribute the connected interface toward CE into VBN v4 under VIF. That's all for CSG. So let's move on AGG. Now let's check the OSPF first. Neighbors are up to CSG and AGG03. So firstly, we also need to enable MPLS on this router. We enable on both interface towards CSG and toward AGG. 0/00 and GI002. Then configure BGP. Because with VPN prefixes toward CSG, AGG will be a route reflector, and so we need to configure CSG as a route reflector client on AGG. When AGG advertise VPN v4 prefixes to Metro Core, we need to set the next hop to the IP address of AGG. It means that we need to set the next hop cell under VPN v4 address family toward a Metro Core router. So for iOS HR, in order for the router to change the BGP attribute, we need to enable the policy for that. So we need to enable BGP policy are enforced modification, so that the router will modify the attribute for BGP. We also need to advertise the back address of IgG under IPv4 address family. We need to advertise the back address of IgG so that this will be advertised to the core network, and then the PE and IgG will reach each other. And activate VPN v4 on this router. Configure neighbor CSG. Remote. Configure Microsoft Safe and Route Reflector client under VPN v4 toward CSG. Let's check the neighbor status. It's okay, and now HGG already received IPv4 prefix from CSG. Now we configure IPv4 BGP label unicast to Metalcore and VPN-v4 to Metalcore. When the IgG advertise VPN-v4 address toward Metalcore, we also need to set the next hop save so that the next hop for the VPN-v4 prefix will be the IP address on IgG. And the same for IPv4 label unicast. That's all. In this lab, we don't use BGP in AGG 203 here. But in production network or in reality, every AGG in the metro network run in BGP because every AGG connects to a ring of CSGs. So in this lab, we only need to enable MPLS in this router. In metro core, firstly, we configure neighbor toward AGG, and for IPv4 label unicast and VBNv4, metro core will act as a R router. So we need to configure AGG as route reflector client. We'll copy the configuration. To be faster, we'll copy configure from HG and paste. So next to advertise the IP address of metro core, we need to advertise the loopback address of metro core so that this address will be advertised into the core network, into RR router, and then the metro core and RR router will reach each other. Then later the neighbor relationship between them will be established. HG. We don't need to use the next hop self here. By default, when the router is distribute the external route received from external neighbor, it won't change the next hop. So the VBNv4 prefixes that the metro core received from our router have a next hop pointing to PE router, and by default metro core router does not change the next hop when advertised to HCG, so we don't need to add the net hop self under the address family. But for the IPv4 label unicast, we need to set the next hop self. If we don't set the next hop self, the next hop will be IP address on interface of the ASPR. Then we need to redistribute this IP address into OSPF so that for AGG can reach the next hop. So we need to add the next hop self under address family IPv4 label unicast toward AGG. Let's check the VBNv4 status. This is up, but no prefixes received. One more thing we forget here is that because AGG is a route reflector client, so we need to add the route reflector client under the neighbor group of AGG for VBNv4 and IPv4. Let's now check the IPv4 refresh again. Okay, this is up now. And already received the IPv4 request, and the next hop right now is pointing to the AGG2 already. So it seems to be okay for the major core neighbor relationship to AGG. And right now we will configure the relationship neighbor, the BGP neighbor relationship to ASPR. The neighbor towards ASPR will use IPv4 label unicast and use the connected interface for neighbor establishment ASPR 01. We use connected interface, connected IP address to establish neighbor, so don't need to use the loopback for update. The interface on the ASPR is 172.16.12.2 ASPR. One more thing we need to configure here is iOS HR. By default, the router does not accept any incoming routes for each BGP neighbor, nor advertise any routes to any BGP if there is no any route policy configured. So we need to configure a route policy under the neighbor configuration towards the ASPR, so that the major core will accept the route from ASPR and advertise routes to ASPR as well. We use a default policy pass over the route. Here we have a default policy that have the default action is passed all the routes. So we will use this policy to apply under BGP configuration towards ASPR. ASPR, something wrong here. Mistake of This is done for configuration towards ASPR. Now move on the configuration for major core to establish neighbor VPN v4 neighbor to RR router. Core. We only need to activate VPN v4 between major core and RR router. And this is a eBGP neighbor, so we also need to configure the policy. And by default, when advertise route VPN v4 route to RR, it will change the next hop to itself, because this is a eBGP neighbor. But here we would like to keep the IP, the next hop for VPN v4 prefixes to the IGG IP addresses. So on major core, we need to activate a feature, enable feature next hop unchanged, so that the major core does not change the next hop when advertising VPN v4 prefixes to RR router. We also use a loopback address of our router for neighbor establishment. And one more thing, by default, the BGP will be established by the connected interface. But in our case, there are multi-hops between Metalcore router and RR, so we need to modify the multi-hop between the Metalcore and RR. Otherwise, the neighbor will not be established. One more thing, with iOS XR, for the inter-AS link, it requires that we configure a static route for a /32 IP prefix of the IP address on the ASBR, so that the MPLS then bind this prefix to a label. Otherwise, if we don't configure this static route, even when the control plan is up but the data plan does not work, so we need to add a static route on Metalcore and ASBR toward the IP address of the other end of link. So on Metalcore, we configure one more thing: route the static and configure IPv4 unicast, and then we address on the ASBR and point to outgoing interface and commit. We also need to enable MPLS on this router, on this interface toward AGG. On the link on the link toward ASBR, we don't enable MPLS, so it is a mistake. So we need to remove this MPLS. No interface. On this interface instead. Here we can see that the MPLS only bind the /32 prefixes to a label. And that's all for Metalcore configuration. And let's move to ASBR. ASBR have two neighbor relationships towards Metalcore and towards our router. We need to activate MPLS first on this router. Zero dot 2.1. We don't need to use this feature, and we also don't need to advertise the loopback on ASBR. No VNV4 address family as well. Metalcore ASBR. Only need to activate IPv4 label unicast. Next hop, save. configure policy, because this is the eBGP neighbor, so also need to configure policy to accept the route. We use IP address of the connected interface for neighbor establishment. What is this file here? Oh, wrong. AS number is 01. Port. Forget to configure first. And the same as on metro router, we also need to add a static route for the IP prefix of the metro core interface. ASPR router static, preferably IPv4 class, and then point to this interface. Need to add a some next mark here, and so MPLS forwarding. And we'll see that the router already bind this prefix to a label to check the BGP neighbor toward metro core. You can see that already received the loopback address on AGG and metro core. That seems to be okay towards the metro core. And then we configure a neighbor toward our router for IPv4 prefix also. One label unicast and next hop self. We need to add next hop self here. Because the ASCBR went forward the IPv4 address, IPv4 prefix to our router, it will modify the next hop to itself. So we need to enable this feature in BGP policy out and enforce modification. Okay. Let's configure on our in our router. We also need to enable MPLS on the interface toward a P router, because if we don't enable MPLS here, the R router and metro core does not reach each other. In that case, we need to advertise the loopback address of our router on ASBR. In our case, we will enable MPLS in interface of our router. Yes, we need to advertise the loopback address of our router so that the major call can reach to the loopback address of our router, so that the neighbor relationship between them will be established. True. We also use the loopback address to establish neighbor with the major call. And need to modify the default EPGP multi-hop. We also need to configure next hop unchanged on the RR towards the major core in order to keep the next hop for the VPN repeats advertised from PE to be the PE address of PE, so that we have a VPN end-to-end VPN connection from AGG to PE. And we also need to add the policy under neighbor configuration to MTC to car. This seems to be okay now. Then we add the neighbor to ASPR for IPv4 label unicast. ASPR IPv4, we use IPv4 because ASPR is a draw reflector client, so we need to configure draw reflector client under the neighbor group of ASPR on our router. And one more thing, we configure the VPN v4 neighbor from RR to PE router. PE and PE router, we configure both VPN v4 neighbor and IPv4 label unicast neighbor. Let's check the neighbor toward M major car. neighbor is still not up. So let's check. We see that the RR still not receive the loopback address of a major core. So there are some issues with the neighbor relationship between RR router and ASPR. Let's check. If there anything wrong on the configure towards ASPR 02 seem to be okay. On the ASPR, we forgot to configure the update source for neighbor establishment. So we will add the update to on the loopback interface when establishment to enable to our router. Yeah, this is already up now. Before you need to have some now we can see that the R router already received the loopback address of major core and check if the neighbor is up. It should be okay. Major core, we already used the update loopback to establish neighbor. In a major core configuration, we forgot to add the loopback address as a source to establish neighbor. That's the reason why the neighbor is not up. Right now the neighbor is still up now. So this is done on our router. You see that the RR already received the IPv4 prefixes from CHE. And then move on configuration for PE router. Firstly, we enable MPLS. Then configure the BGP to establish a VPN neighbor relationship with RR, and as well as IPv4. We will configure the BGP on PE towards RR router 65001. We don't need to use this information, and need to advertise this loopback address of PE router into IPv4. IPv4 label unicast. For this neighbor, we advertise the loopback address and enable VPN and configure neighbor toward RR router. We enable both address family of VPN and IPv4 label unicast toward RR router, and configure the loopback address of RR router as a source for neighbor establishment. Yeah, the label is up already. We need to configure VRF on PE router and then apply to the interface. And under VRF, actually the RR router already advertised the IPv4 prefix to the PE, but on the PE router it hasn't configured VRF for route target import, so it does not import the IPv4 prefix into its route table. So we configure VRF first. VRF import zero 1. We need to import the route that advertised from CHE with the route target is 65001. Configure on CHE. Import 6010 6501001. Then we apply this to interface. Interface G0001. no IP address. We need to remove IP address first before configure VIF for this interface. And then add the IP address again. It's okay. Right now we need to redistribute the IP address on the interface connect to the CE router into BGP. VIF signaling, and we need to configure RD for this VIF. So, and then we will distribute the connected interface, redistribute connected interface into BGP under a VIF. So now let's check VPN4 route again. So we see that the route, the PE already import the IPv4 request sent from CHE. Let's check on the CHE. It does not receive a route that advertised from PE router because in VIF we has not imported the route target that configure under VIF on PE router, so we need to configure the route target import for the value that export from PE router, that is 65001:11. Let's check again. The CHE already received the IPv4 VPN4 request from PE, so the connectivity between CA2 to CA1 should be reachable now. Here we can see that we can ping from CA2 to CA1. So let's check the forwarding data on CHE. Let's check forwarding data begin on CHE. Here, let's say that when the CHE want to go to the destination prefix at 172.16.100.0/3, that is a VPN prefix on PE1, it will forward to the next hop is 10.0.2.1.1 at the AGG and use a VPN label 24007. This is the VPN label, and when this packet arrived at AGG, the AGG will check its VPN table. From the VPN table, we can see that in from HGG. If we want to go to this prefix, VPN prefix, it will send to the next hop at the IP address of 10.0.1.1. That is the loopback address of PE router, and use the label 24007. That is the VPN label advertised by PE1. But in order to go to the IP address, loopback address of PE1, the HGG should use the IPv4 BGP IPv4 label. So we check IPv4 label. It said that if he wants to go to the loopback address of the PE1, it will send to the next hop address of 10.2.0.1 of this is the IP address of Metro car, and use the label 24002. That is the label unicast. And in order to send the packet to a Metro car, the HGG will send to the next hop is HGG 03 and add another label. That is the LDP label. When the HGG send the packet to the next hop is at 10.0.2.0.1, that is the IP address on the HGG 03, and it use another label number 16. So the packet going out of the HGG, there are 3 labels in its stack. The first is the VPN label 24007, and then the BGP IPv4 label, which is 24002, and at the top will be the LDP label. We can check with the Wireshark to see the label of the packets going out of HGG. Here is the ICMP request message sending from the CA2 to CA1. We see that there are 3 labels in the label stack. They are like what we have seen in the display of the configuration. The first VPN label 24007, and the next is the BGP IPv4 label 24002, and at the top is the LDP label 16. The packet when arrive at the HGG 3, HGG will check its forwarding table, and the packet go to the HGG 03. HGG 03 will check its MPLS forwarding table for the next hop 10.2.0.1 at the Metro car, and it will pop the LDP label and forward to the Apple interface A00, because when HGG forward the packet to PE1, the next hop is MTC, the Metro car here. So the HGG is the last hop to reach the Metro car router, so it will remove the LDP label and forward to the Metro car with only 2 labels left, which are VPN-v4 label and BGP label. The Metro car router, when receive a packet with 2 label, VPN label and BGP IPv4 label, it will check in its MPLS forwarding table, and then it will swap, because this is a packet destined to the address of PE1 router, and this prefix, because this IPv4 prefix advertised by PE1 and together with the BGP IPv4 label. So when Metro car router forward the packet toward PE1, it will swap the BGP IPv4 label from 24002 to 24000. We can check with the Wireshark to confirm the stack. Here we can see only two labels left. The first is VPN label and the second is BGP IPv4 label. This packet, when arrived at ASPR will check in its MPLS forwarding a table for the destination of P1, and it will swap from BGP IPv4 label to LDP label of 18, and then forward the packet to P router through the algorithm interface 000, and the P router then removed this LDP label because P router is the last hop to reach the P router, so it will remove the LDP label and leaves only VPN label. You can confirm the stack by checking Wireshark on the interface algorithm of P router. Here we see only VPN label left on the algorithm interface of P router, and when the packet arrives at PE01, it will remove the VPN label and then forward the IP packet to CE-A1. That is all the configuration for the Metro network to establish an end-to-end VPN from HGG to PE router. On the PE, we can see that with the VPN prefix that it received from a CHG, the next hop is the API address of HGG router. So we have a VPN connection from HGG to PE run across the border between two AS. That is all for the configuration of the Metro network. Thank you for watching the video.